Hello, everyone. Thank you for having me. I'm really excited to be here. I'm Ya Yundu, a postdoc at Professor John Rogers' lab at Northwestern University. I got my PhD from UCLA in robotics and control. Today, I'm going to talk about my past and current work and future plans about edge AI enhanced resource-limited systems from robotics to bioelectronics. As you know, Industry 4.0 brings all kinds of autonomous systems, such as autonomous cars, robots automating manufacturing, etc. Now, Industry 5.0 is coming, whose core is seamless human-robot interaction, also known as HRI, to maximize efficiency. This requires the robot to work in unstructured environment, for example, flat surfaces, with integrated design, perception, and control. As human is part of the dynamic environment, current key problem, lack of human science in HRI needs to be solved. Robots usually don't sense people's physical and mental health. For example, the worker might have an acute heart attack during work. If the robot doesn't detect it, it not only cannot save the worker's life, but also can hurt him or her even further. If the robot can feel human health, for example, heart rate, respiration, and mental stress, and even intention multimodally, they can show empathy, act to collaborate. So making people feel safe and comfortable. Adding human science also enable robots and humans to learn to adapt to each other based on their statuses. To achieve seamless HRI, we have to fill an information gap. Technology experts, they are really good at creating sensors and robots at a low cost, but they don't know how to interpret sensory information for human emotion, cognition, and behavior recognition. While on the other side, human science experts, they know how to interpret those information, but they don't know how new technological methods could address their bigger challenges. For example, different disease detection, including cancer detection, for example. Of course, they don't know how to integrate human science with systems such as robots. My research is at the intersection of mechanical engineering, electrical engineering, computer science, and biomedical engineering to develop working systems in unstructured environment, as I just said, and resource-limited conditions. For example, most mobile robots have limited onboard memory and computation power, and also for the biosensors, they need to work in realistic conditions. For example, the hospitals, they have hundreds of Bluetooth, wandering around, so you have to have really stable connection. So, which is as important as knowing human-centered design to identify limitations and opportunities of technology. Also, we need to know the big picture of human science and healthcare problems and the practice needs. As a researcher, I work at the intersection of all of them. So we are faced with some major challenges, which ultimately theme and underpin the basis of my research. So the first comes from the robotic side. We need to develop robots that can work in unstructured environments with resource-limited systems. From the bioelectronic side, we have to capture meaningful information that reflects human true physiology and translates into behavior. This is very important as human science and healthcare experts, as I mentioned just now. So sometimes we have to introduce new technology and actively show them what actually be possible. So now some research I'm going to show you later today, is actually doctors actually don't think that it's practically necessary or useful until we develop the technology and show them the data in terms of data matter. Plus, the way we build those systems have to be deployable and scalable. The meantime, the accuracy of the systems have to be usable and in resource-limited settings, as I just mentioned, within current and future regulatory needs. So at the end of the day, balancing all of this makes this so challenging. So my research focuses on optimizing design in hardware and software to develop autonomous robots and a new class of medical devices to capture human science and healthcare. And in seamless HRI. So, and in my work, I focus on developing novel end-to-end hardware and software systems to aim to fill the clinical and practical gaps. To do that, I conducted large-scale clinical and natural living studies by collaborating with health organizations and various clinicians nationally and internationally. Also, I've conducted explainable machine learning, and now currently I am exploring and will continue to explore explainable real-time machine learning and advanced control to incorporate the multimodal signals into safe, comfortable, and efficient HRI. Before diving into my detailed research, I'd like to introduce the concept edge AI. Different from traditional AI and machine learning applications where data is sent to centralized cloud servers for processing and analysis. Edge AI, on the other hand, brings the computation closer to the data source. This means the data is processed locally on devices such as smartphones, wearable devices that I'm going to introduce later, or on edge server without the need for a constant Wi-Fi or internet connection. Without sending the data to a server and receiving a response, this is crucial to reduce latency and protects better data privacy. One highlight of my work is edge AI-enabled resource-limited systems. All right, let's move on to my work. During PhD and postdoc interdisciplinary work in bio-inspired software robots that I don't have time to cover today, but I will talk tomorrow. I published field robotics, I'm gonna cover today, and bioelectronics. So I published and submitted 9 first authored and 4 co-authored articles in top peer-reviewed journals and conferences, such as Science Translational Medicine, Lancet Digital Health, and IEEE Robotics and Automation Letters, etc. And I got 1 patent with several high-impact ones in preparation. Also, my work was a finalist for 2 Best Paper Awards for International Conference on Intelligent Robots and Systems, also known as IROS 2021. Let's dive into the first part. As an example of mobile robots I developed, here I'll introduce the low-cost under canopy, i.e. the robots work under the plants. Autonomous robots as mobile agricultural platforms. In agriculture, weeds are the biggest headache of farmers as they compete with the crops for resources and reduce yields. To kill weeds, farmers spray the entire field with herbicides, which can harm the environment and human health. Also, more and more weeds become herbicide resistant. So robots for precision weed control are urgently needed. My own drive to innovate in this space actually is personal. I was born in a rural Chinese village, and I recall like countless hot summers that I helped my parents weed by hand in the fields. I still recall the feeling of the sting of corn leaves on my skin and the sweat biting my wounds. Sorry, I'm still like getting the good skin right now, even if I recall. So yeah, existing agriculture machines are typically large, suited only for wide row spacing, wide row crops, and rely on GPS with limited precision. TerraSynthia is compact, but only navigates well in wide row spacings as well as because they rely on LiDAR for like between row navigation. The robot from Eco Robotics works in narrow row spacings, but all the platforms only work in the early stage with very low weed density. But then you might ask me, why narrow row spacing is so important? Because the crops like pepper, garlic, soybean, and flax, and so on, they have the between row spacing 20 to 45 centimeters. So then North Dakota here, where we test our robot, contributed 91% of the US flax production. Only US market for the flaxseed oil in 2020 is $1.12 billion. As such, here comes our robot. Our robot navigates successfully and robustly in narrow row spacing and performs autonomous end-canopy weeding. So here's one experimental demo of our SandBot in flaxseed fields. We tested 3 summers in the fields. We automated its operation, including charging, navigation, and localization, leveraging sensor fusion techniques that integrate computer vision, IMU, and GPS. It also autonomously detects and sprays weeds using a deep learning model optimized for embedded systems. So the machine learning model is deployed on board and scan and predict the weed it sees in real time. As you can see, this is the top view, and this is the side view. When it sees the weed, and then recognize, predict on board in real time, and split the corresponding RB size. There are 2 RB sizes here. So here are some details of our robot's hardware. We designed the chassis for the robot to pass bumps and dents in fields with heavy components such as powerful DC motors and water tank and batteries at the bottom to lower its gravity center. There are 2 sprayers at the back, each one fixed with 1 pump for pressure spraying here, and 1 gimbal for spraying wide angle, and a camera for weed detection. 1 camera with a stabilizing gimbal at the front for autonomous navigation working with MU. So the pumps and also the motors with the encoder, gimbal are controlled by Arduino Uno here. It's a low level control, while the Jetson Xavier is a high level, controls the high level logic, such as autonomous charging, navigation, and weed identification. We use a 3D printed shell for dust prevention, which is not shown here. Due to system complexity, I only cover 2 highlighted parts of our algorithms: embedded system deployable weed detection and localization through sensor fusion. First, let's see how our robot detects weeds. Different from physically bulky and expensive spectrometers, the low cost of RGB cameras increase the computation power, and advancements in deep learning make image-based detection on mobile robots possible. However, most existing crop weed libraries are built from photos taken from indoor labs without shadow and noisy backgrounds, which actually exist in realistic fields. Based on the collected libraries released the work, either use simple models to classify crops and weeds areas in images, but they can't really classify what kind of weeds. Or they use deep learning models, specifically pixel-wise segmentation convolutional neural network, or also known as CNN, to detect weeds. But please note that their experimental platforms are big vehicles with cameras underneath the chassis and extra artificial lighting to maintain the stable lighting conditions. But these models are too computationally expensive to run on compact robots. In summary, libraries for crops and weeds taken from realistic fields are missing. Existing models are either too rudimentary to work in realistic fields or too computationally expensive and only applicable to large machineries. As such, here comes our robot, a robot that can work robustly and low cost for under canopy weeding. First, we contributed the first large annotated realistic dataset with 40 most common weeds in fields and gardens, collected from 20 locations with 1 or multiple kinds of weeds in 1 image. As you can see, this is from the image library. They are taken under different weather and light conditions. And then before training our machine learning model, we performed various operations to augment the images so that the robot can recognize the same weed under different lighting conditions, under different weather conditions from different angles. We modified the off-the-shelf MobileNet V2, a lightweight CNN model, and choose the weed with the maximum probability as the prediction result. Here we present the top 5 models that give the best performance trained on our library. As we can see, modified MobileNet V2 has the least parameters with only 5% accuracy drop, the dashed line here at the bottom, while its training time and memory taken is roughly 1/5 or like to 1/4 of the other more complicated models. So next highlight is the localization. So how the robot knows where it itself is in the larger fields. So here comes our most recent contribution. First, we collected and open sourced again a unusual inertia navigation dataset, including 3 phases. The first one is indoor with the object track on the wall capture, and this one is the outdoor artificial fields. Actually, I grew this field on the roof of the engineering building at UCLA. So I grow the flags and build the field. And the last stage is the outdoor realistic large strawberry farms. Also, we have a drone flying on top of our robot while the robot moves in the fields to capture the ground truth where the robot is in real time. So actually there are chest markers for calibration, And then, so I don't have time to cover today. So since the drone captured the videos, we developed a automated 2D ground truth robot position tracking from the recordings. And then also last thing is that we develop a neural extended coming filter for robust localization with the smallest error that I'm going to talk about next, very briefly. There are so many details, but I'm going to try to deliver the idea as briefly as possible. So previous work have shown that a neural network can learn the displacement of the robot and also the heading of it by that's a neural network, by including the information from accelerometer and a gyroscope from IMU. But they have problems because they can affected by gravity pollution, also high frequency inertia signature. What I mean sometimes in your measurement, you have really almost go to infinity acceleration, right? If you let the neural network learn it, it will drift away. And then also it can, based on the sensor orientation on the robot, it has different results. For the heading rate singularity, so they cannot differentiate whether the robot is like 0 degrees and 180 degrees, whether the robot is moving forward or backward. So for our approach, we solve the problem by two very important highlights. First one is add the magnetometer from the MU, the same MU, just add a magnetometer for the global anchor. So essentially, which is related to a global magnetic field. And also, in order to avoid the drift from the high frequency inertia signatures, we divided the modes of the robot into 3 modes: constant moving, or accelerating, or decelerating. So by that way, we actually avoid the continuous integration of infinity, so that you don't drift away. So this, there is a lot of math, but I will develop the idea here. So what I just showed is a neural inertia navigation model. And then once we write out the state space of the system, actually you can find that the state space is a nonlinear function of the control states right here. The G is a nonlinear function. And the great thing is that the y theta here is what we just saw from the neural network we developed. And then the G can be right a function of the y theta. So correlated with the neural network. What does that mean? Means in Kalman propagation and update, especially propagation, you need to update your covariance matrix. So then once your neural network learns the y theta, and then you can get your G. So by the neural network gradient algorithm, so we can calculate the gradient of G to U. So essentially, when the neural network learns the gradient, the dynamics of the system got updated. You can update the covariance, and then you can update the propagation. So which means the neural network is not learning like black box, but it's learning dynamics of the system. So finally, we realize like roughly 2 times less parameter numbers with a lightweight neural network, and with almost 5 times higher tracking resolution. As you can see, the blue lines here is the ground truth. The yellow or like orange line is our result, neural Kalman filter. So they are matching with each other, following with each other, while other state-of-the-art algorithms are drifting away. Even the GPS are out for 20 minutes. We are able to realize 2.75 meters resolution. Okay, now let's go over our approach for autonomous agri-robots. Unlike a giant machinery, our robots need to be small to work under the plants and compact with the limited computation power. So we co-developed the hardware and the software. To compensate the sensitivity to light conditions of computer vision-based algorithm, which is a general problem, we collected and open sourced video and navigation libraries from realistic fields, and also light neural network, developed a light neural network for precision weight control and a robust localization with the sensor fusion. Though I don't have time to cover our inter-row navigation and autonomous charging approach, etc., we can already see that such platforms require intertwining hardware and software, hardware design and perception and control algorithm development. Okay, as a postdoc at a Rogers Group, I gained access to state-of-the-art facilities, a network of collaborators from 4 countries, 6 labs, 3 hospitals, and interfaced with 3 startups. The 5 projects I've been leading cover mechanical, electrical, and acoustic fields with applications in neural, cardiovascular, pulmonary, and muscle health monitoring and disease detection during sleep, under pain, exercising, singing, and seizures from hundreds of adults, babies, and animals. Conventional wired systems like EEG that track brain activity and a vocal dosimeter to monitor vocal usage hinder continuous health monitoring due to their tethered nature. Commercial products like Apple Watch use ECG, or you call it EKG, i.e. cardio wave monitoring, if you put your hands on the crowd. However, it's kind of sad that only people over 21 can use this function. I got to know this by accident because my undergrad was soldering my board, say, hey, you know that? I want to use the Apple Watch, but one day I put it on, I cannot use it. I said, why? Because he said, I'm not over 21. I was like, oh, I didn't know that previously, But yeah, it's glad to know. So as a researcher, I aim to develop new generation wireless, low power bioelectronics for healthcare, making them accessible to all ages and a wide range of wealth. Those are sensors I developed. For seamless HRI, if you recall, we got to monitor signals and intentions from human. So next, I'm gonna first present my postdoc work on explainable AI-enabled word-based sleep study. One project that I've led, finished, and submitted. Why are we interested in sleep study? We spend 1/3 our life sleep. And a good sleep is crucial for a strong immune system, better mood and energy, and the body's healing process. It improves the brain function like alertness, decision-making, and problem solving, and it reduces the risk of chronic diseases. Yet, what happens during sleep remains largely unknown. American Heart Association, known as AHA's checklist for optimal cardiovascular health is updated. Now it's called Life's Essential 8, adding healthy sleep, besides no smoking, blood pressure control, etc. Compared with the traditional sleep labs, at the hospital, each night costs $1,500 per night per person. So the the at risk, the commercial wearable devices at risk offer at-home sleep monitoring, but has long sleep onset latency, as they normally indicate sleep if you don't move much. For example, Fitbit, which has been shut down by Google already. But when you haven't moved for about 1 hour, they treat you asleep. And respiration tracking, i.e. breathing, because they are the wrist, so definitely they are not tracking that, right? So which actually is important, I'm gonna show you, is missing from those sensors. So we use mechanoacoustics, which also known as MA sensor, released by previous lab members, and attach the sensor at the super astral notch for the sleep study. So super astral notch, if you put your fingers there, you can easily feel your heartbeats, check the moments for breathing, vibration while talking, speaking, swallowing, coughing, etc., and also even body orientation and body motion, even gaze. Why? Because the core components for sensing is a inertial measurement unit, high sensitivity IMU. So the well-encapsulated sensor uses a silicon elastomer attached to the epidermis, i.e. the skin, can detect the activities of underskin tissues and organs. So we can encapture the MA with the silicon elastomer and analyze the mechanical properties to keep stable performance after repeated peeling and bending. So by collaborating with the clinicians at a Carl Foundation Hospital, we collected 43 nights with our MA sensors. It has onboard memory. Oh, actually, this is me at the hospital wearing the 3 sensors, our sensors circle out here, and also the wired system traditional sleep lab. Actually, I have the EEG electrodes on my head, also the ECG on my chest, and also the pulse rate stuff, and then also the ribbon to measure my respiration on my belly and also my chest. So very cumbersome. Our sensor has the onboard memory to store data or real-time data streaming and plotting on iOS device. As you can see here, those periodical here, as you can see, is a respiration, my inhale and exhale. And also you can't really see very obviously, but I can show you a bit. And then there's a very small sharp peaks. That's my heart sounds. So we also have a cloud server that support remote monitoring of the sensor status and the signals. So even if, let's say, kilometers away, the doctors deploy the sensors, I can see on our cloud server within 2 minutes, delay, I can see the sensor status, how much battery is left, and also how well the signal looks like, how much memory is left, like that. Here's one night sleep data. So from only 3 axes, I want to emphasize this, only 3 axis accelerometer from the MU, we can see, this is the one sleep night data. We can extract if we zoom into the raw signal, we can see the user's heartbeats. As you can see, these are the heart sound, S1, S2, S1, S2. And respiration here, activity. From the activity, we are able to calculate the human's body orientation, whether it's facing up, left, or right, or even how much they move, whether they go to the restroom or not. So snoring and sleep apnea. Sleep apnea is a disorder actually is where the patients or the user stop breathing and restart again, periodically. With our signal processing algorithm, I'm going to introduce, I don't have time to cover actually today. We are able to calculate the heart rate, respiration rate based on our MA signal, which is showing in red lines here. And also they match really well, as you can see, compared with the gold standard, which are blue lines here. They match really well, heart rate and respiration rate. And then I want to explain a little bit, what does the heart sounds mean? Actually, in our heart, sorry, I have to switch the pointer to be able to click here, the signal, okay, here. So we have the tricuspid valve and a mitral valve. If they close, the S1 sound appears. And then we also have the pulmonary valve and the aortic valve. When they close, during the heartbeats, the S2 sound appears, as you can see here. So they will repeatedly S1, S2, S1, S2. Each heartbeat is associated with 1, S1, and S2. So yeah, our first contribution is the signal processing pipeline that I don't have time to talk here today. Extracts 146 cardiopulmonary and activity features covering time, frequency, geometry, and the nonlinear domains instead of just one number. Then you might ask, why do we need so many features? Those features actually correlate with your neural system body. So for example, based on the medical field study, frequency domain signals, for example, which is really frequency domain about the heart rate variability signals, when there is a very low frequency, they are correlated with the sympathetic nervous system, also as known as SNS, the nervous system, which prepare our body for stressless activities, fight or flight. While the high frequency signals are correlated with our parasympathetic nervous system, which help us rest and digest. So that's why we have to develop the signals not only in time domain, but frequency domain, also geometry domain and nonlinear domain. More specifically, for example, the feature we developed, the mean coefficient of variation, breath interval here, in time domain related to respiration rate variability here has a close correlation with the occurrence of rapid eye movement stages called REM stages. Essentially, it's during that stage, your eyes move a lot. That's why they got the name. Those are shown in the green blocks here. And you can see every time there is a peak in the blue lines here, there is a REM stage appears, right? Similarly, also the MCSI feature from heart rate variability, which is shown in the pink lines, has a high correlation with the wake-ups during sleep. As you can see, every time there is an increase and drop, increase and drop, increase and drop, then people wake up. So yeah, that's why we need so many different features to predict different sleep stages. You are in light sleep or deep sleep. These features are then input into our MA SleepNet, which is our second contribution. The highlight here, the structure is so complicated, I don't want to cover all of them, but then the highlight here is the autoencoder structure here and the attention mechanism in our MA SleepNet. Why? Remember, we have 146 physiological features, right? The autoencoder, the dimension is also 146. What does that mean? Means, okay, now all the information comes through and I go through here and predict the sleep stages. When we track back here, from here, we do the gradient-based method. We look at the weights. What that means we know how much each feature contribute to the sleep stage prediction, positively, negatively, and how fast they adapt. So then here we can see the respiration rate variability, RRV features, shown in blue bars here, contributed most to the rapid eye moment and the non-rapid eye moment. So REM, non-REM stage differentiation. While activity features and RRV features marked in yellow here lead the sleep awake differentiation. So according to our results, now we know why the active watch at wrist cannot monitor sleep stage well, because it lacks respiration, which is the most important in sleep stage differentiation, even the sleep awake differentiation. So to further rationalize, so you think we said our deep learning is explainable instead of black box, but you have to show more, right? To further rationalize our deep learning results, we plotted the Barley plots of the top 2 most important features and the least 2 important features is stage sleep stage differentiation. It's visually obvious the distribution of the first 2 features at the different stages is more distinct than the other 2. So this is statistical analysis without any deep learning involved. So this means our deep learning model is learning the correct information instead of just learning random stuff. We also run another most commonly used deep learning model for feature importance analysis. The results are similar. As you can see, RRV features are taking the dominant role in differentiating REM and non-REM. Activity features and RRV are taking the leading role with the sleep awake differentiation. Then you might ask, why, since those are existing deep learning model can do that, why do you need your model? Because our models are explainable, but those are not explainable. Confirming the results from our deep learning models are reasonable. So when compared with the most recent sleep studies with the state-of-the-art simple sensors, as you can see here, this was published in 2023, Science Advances. Our sensors much better than theirs. As you can see, 95%, 80%, and 91, 92. But then they show that their study beats others. We show ours outperform theirs. So, and one thing to notice that is the REM detection, ours reach 91%, which is very important. Why people care about REM? Because when it comes to we talk with doctors, they care about REM a lot because it's important in our memory consolidation, emotion control, and also it shows correlation with the depression. So it's very important. Our sensor, our algorithm can detect 91%. It's actually, I can show you later, is better than human. So this everything owes our MA sensor plus feature engineering plus explainable machine learning. So another highlight from our study is that we collected 5 nights from a female, YY, is me, Yayun, and a BG, a male, from the hospital. The result obtained from our MA SleepNet trained on a 30-night other people's data and tested on YY and BG's 1-night data can be much worse than only 4 nights YY and BG's data and tested on their another night data. So this actually acts as a buzzer for the sleep community. Instead of collecting more diverse data from more people, why don't you focus on collecting data from one person for multiple nights, right? And then, but people will complain, okay, every night is like costs $1,500. Of course, how insurance can cover that, right? I mean, for the long run, definitely, we are still looking for how can we develop the best wearable that can differentiate the sleep stages, right? But this actually, at least points out the direction. So also one thing to emphasize that our approach can realize 88% REM, just now the 91% is based on 6 people, we compare with other studies, benchmarks. And then now it's overall 43 nights actually. We are able to realize 88% rapid eye REM prediction accuracy comparable to technicians 87%. So even better than human. So last thing is we utilized lightweight machine learning algorithms on our MA signals and it realized the 93.8% precision for sleep apnea detection. So we can detect when human have sleep apnea. Then by adding an actuator, we can wake people up so that if they don't recovers the breathing, which is a disaster. So yeah, that helps in practice, but I don't have time to show here today. So until now, I covered the algorithms and AI like on our MA sensor during the sleep study. But as I mentioned, the MA sensor was released by previous colleagues. But I want to emphasize here is that the MA sensor was, although it was released by previous lab members, the hardware and the firmware for my study was everything was developed by my team. Because for the circuit side, we are safe by adding that will never burn the patients, and also very low, like I would say, theoretically the lowest power consumption. Also, we updated the antenna design so they can charge wirelessly really fast. And also firmware development wise, in order to mostly efficiently interact with the CPU, we wrote the firmware easily, like more than 40,000 lines, in Rust. So different from C because it can because that interacts with the Cortex M4 CPU better. And also we have embedded the filters on the sensor, like for example the common filter, also fast Fourier transforms stuff. Those calculations are on the sensor. Also, the sensor have a higher signal noise ratio. So one thing we want to mention is that actually by by itself, it can be published as a computer science paper because we have the data compression algorithm. What does that mean? So we have like a 10 to 60 times data compression. So for example, this is your signal from your sensor. If, for example, your signal is like from 1,000 to 1,000.2. So by purely saving those like absolute value, 1,000, you take a lot of memory already, right? So what we want to do is actually, if your signal is not changing that much, so we save the first initial state, 1,000, and then we store the relative change plus 0.2. So next is 1,000.2, right? And then minus 2.1. So by doing that, we save a lot of memory. Of course, we save the power consumption because when through Bluetooth, when you transfer the data, you save a lot of memory, you save a lot of power, right? So because the Bluetooth is the most power consuming part. So by a 50 mAh LiPo battery, so it's a smaller, it's like this large, it can realize 10.4 days because in saving mode, because we have two modes actually. I'm closely collaborating with the people in Europe, right? Yeah, if I ship the sensor there, so I click a button, so power saving, it lasts 10.4 days. If you continuously, activate the motor, activate the sensor, collect data, and real-time streaming, it lasts 4.3 days, which is we cannot see from commercial products now. And 1.3 days for the memory storage. So yeah, so as I mentioned, MA might not be the best sensor for it. And then for the gold standard, in the sleep lab, they have EEG, ECG, EOG, EMG even. So then I'm going to introduce next about low power multi-modal bioelectronics for health monitoring and disease detection and human-robot interaction, covering what I just mentioned, those functions. So when it comes to multimodal wireless smart sensing, what do we think? You will think about the signals, electrophysiological signals like EEG, EOG, your eye movement, ECG, cardio, EMG, muscle, and physical signals like body temperature, body movement, and also skin hydration. Also biochemical signals, blood glucose, and sweat composition, etc. And photoelectrical signals like PPG and blood pressure. So during my postdoc, apart from this one, biochemical signals, because I'm not a biochemical person, not a biology, not a chemistry. So apart from this part, I lead this part, the electrophysiological signal I'm going to cover next. Other parts, all the sensors here, I lead or get involved in designing the sensors here. With applications in physiological parameter monitoring, actually, I'm going to talk tomorrow in my vision. How can I get my first NSF proposal based on that? And also with applications, in drug delivery and human-robot interaction. So yeah, so let's talk about another project that I've been leading. So developing a multi-model, wearable EXG SCG sensor. I call it EXG because it can work as an EEG to measure the brain wave, EOG movement, eye movement, ECG, the cardio, and the EMG muscle. That's why I call it EXG. SCG, seismal cardiography, is based on vibration. Actually, the MA sensor whose core is IMU, I just showing you, it's already actually is kind of SCG. So, and then as you can see here, let me introduce as EEG first. Our EEG has been deployed to 30 seizure patients already. This is our small sensor. The picture on the patient's head, while those other wires are from the hospital, the gold standard system. This is the sensor on my this picture of the sensor on my hand. The sensor is, as I said, deployed to 30 patients clinically already. Here are some figures showing the performance. So the top is you can see our sensor matched really well with the gold standard in time domain and frequency domain. You can see those small brain waves. You can see the same. The left side is the gold standard data. The right side is our EXG data. They capture the same brain activity in the same frequency band. So one thing you notice is here, actually some data is missing in the gold standard. Why? Because they're wired. They restrict the patients from moving around. So then when they move around, the wire get disconnected, and then they lose the signal. But while ours is wireless, continuous recording. So that's actually one strength. So if attach our same sensor, but different geometry, as you can see here, if attach the chest, our sensor can measure the heart sounds, as you already know previously, as well as and also the ECG. ECG essentially the electrocardio signals when your heart beats. ECG should have specific time difference between your heart sounds S1 and S2. If the time difference is different, means what? Means why the time differences should be almost the same, because it takes a specific time for your valves to open and close, right? If the time is different, means the valve has some problems. That's why our sensor have deployed 2 hospitals right now to by collaborating with professors and doctors in cardiovascular disease detection. And then this is actually the same sensor, but different configuration have been deployed onto neonates, validated on neonates and adults to measure the muscle activity, called EMG SCG. So actually, this is one of the biggest demo in this year. I've done February 14th, last month. And so I'm not allowed to show the data here. It brought more than $10 million donation to John. John was so excited. Because the same sensor was tested on a 5-week-old baby to see their muscle activity. We actually competed with the largest, as you can see here. That's the largest commercial product in this field, Delsis. One day, actually, by collaborating with the Shirley Ryan Ability Lab, you probably know the number one rehab hospital or lab in in Chicago. Shirley, who the establisher of the owner of the hospital, one day she told John, say, she was watching a soccer game, right? The athletes got sweaty and see the muscle movements and stuff, but when child's parent coming in, so actually my child has some disease for muscle development. If we know early stage, we could have prevented that. John, could you develop such kind of sensor? Then the problem is for this Delsis, number one in this field, they have good performance, as you can see here. The top is their signal, at the bottom is our signal. From the magnitude, they're similar. But in the hospital, because there are hundreds of Bluetooth wandering around, they have really bad connection. They couldn't even connect really well. But on that day, 6 of my sensors on the baby, different parts, the thighs, the glutes stuff, different positions, they capture really nice signals. All the doctors and also Shirley got so excited, and also they stream really well in real time with one iOS device. So everyone got a surprise, and then I guess, finally the money flows in, although it's nothing related to me, but John was super happy and I sent 2 very big thank you emails after the demos. It couldn't be more fantastic. But overall, it shows how our sensor works as to monitor the muscle activity. Overall, when it comes to design, you already see that's a sensor, like a design for different multi-purpose. You already see. The highlights are several aspects. First thing, we add a mesh layer to prevent a mechanical overstretch. What does that mean? Means, so this one, so the distance between here, those 2 electrodes actually can cover any 2 points on adult scalp. For EEG usage. So then if you, they can realize 13% strain. I don't remember how many times by collaborating with the doctors, we found our sensors in the trash can. So yeah, to prevent them from overstretch or broken. So that's why we added the mesh layer to strengthen them. Also, it's geometrically adaptive, as I just mentioned. Those can be to EEG. If you want ECG here, the same geometry follows. Outside, also there is one more function I didn't mention. It's got a galvanic skin response. Essentially, can measure how nervous people are by using those two electrodes. If you want to cut them, cut here, all the electrodes here, you can directly solder the electrodes out of those metal panel paths. You can work as EMG, as you just saw on the babies. So finally, also technically, we want to mention that hardware and firmware all optimization done by me and my undergraduate and master student. We realized 12 times the life length per charge of state-of-the-art with the same commercial sensors with the same size and weight. So they lasted for 24 hours. We lasted 12 days. And also they don't offer the real-time data streaming, but we do. So also the same thing, as you can see, since you can measure the cardio, the brain, the muscle, and also the eye movement. That's actually really cool stuff. We found collaborators who are interested. So by using surgical robots, they have to be able to detect human's gaze. But the commercial products cannot realize that, but our sensor can realize really high resolution. That's probably also my first NIH 21, the Blazer proposal. So yeah, so by attaching the sensors at different positions, we are applying right now. I have an ongoing project with my undergraduate hired from mechanical engineering for human-robot interaction. What we want to do actually is for on a autonomous factory setup. How can robot and human work seamlessly for maximum efficiency? Human can teach the robot, and then from the human's physiology, you can see how human was satisfied with the performance of the robot. And if the human got tired, the robot can take over tasks, etc. But I don't show details here based on the time. And then also besides wearables, I also work on implantable batteryless EXG for cardiovascular signals monitoring. So as you can see, the signal, the animal can move freely inside the cage. And then with our sensor monitoring, it's ECG, and also activity during routine activity, and also drug test. A month ago, we tested we injected different cancer drug, and I see how they respond. And then finally, it's at work as a preclinical trials before putting on human, right? So as you can see here, the raw signal here, even without any filter, is so clear. And then just John got so excited. And then also by applying some hydrogel. That's one thing. Is this sensor is exposed after 1 month. Actually, we cut it open, so the electrodes attach so well on the muscle. So we have hydrogel highlights there as well. So yeah, so overall we have high signal quality. One highlight is that our sensor lasts for 1 month, while the commercial products can only last for 1 month. And then also this one, the exciting part is that we have a 2-channel version. This will be the first one in this field. We think will revolutionize the cardio neural muscle studies on mice. What that mean? Means you can put a 1 channel on the head to measure the brain signal, and a 1 on the cardio. So you can see actually when people, for example, to simulate when people have a heart attack, how your EEG responds. Also 1 on the muscle, for example, on your stomach. If you have a stomach ache, how the signal respond, your brain, reacts, and also how your cardio reacts. Stuff. So I presented this one 2 months ago at a international conference, neuro conference. 100 of the researchers say, oh, if this can be commercialized, a lot of people, really want to use that, because this will be the first one in mice, because the size is very the restriction and the functionality for sure, right? Also, the same platform also being applied for human heart blood occlusion detection. So yeah, I also involved in pressure sensor, optoelectronics, and a pediatric pain study, etc. So now you've seen my past and current work. Let's look forward. So my future lab, as illustrated in this figure, aims to develop multi-model, adaptive, and a comfortable system through 3 innovative approaches. First one is developing multi-model electronic wearable and implantable devices for healthcare monitoring, early disease detection, and new brain insights development, such as neuroplasticity after stroke, and also during the rehabilitation. Second, developing hardware and learning and control strategies under uncertainty to enhance the interaction of robots with humans, with humans comfortable. So actually, those will be two directions of my first two PhD students. For those two parts, we'll be extensively collaborating with the clinicians and also the experts in biology, medical fields, even maybe music. I will talk a little about in the next slide. And then third one, during the process, we'll be implementing the edge computing and explainable machine learning algorithms to integrate the human health and the intentions, integrating all of this for evolutionary safe and adaptive human-robot interaction. Overall, my lab research is obviously very interdisciplinary, and like our approach for this is mechanical, electronics, computing integration. Yeah, this is actually potential collaborations at a CU border. As I mentioned, we will collaborate with people from physiology, psychology, and also since the human-robot interaction, we will need the GUI, the graphic user interface design. So we collaborate with the people who are really good at UI design. Also, we're trying to make the wearables more comfortable, right? We want to collaborate with the people from textile, like expertise, and also music, as I mentioned, like psychology, etc. So yeah, finally, I want to thank you, say thank you to my community, which without them, I couldn't succeed in my research or even my job, search. And also the agents, and also undergrad, my powerful, like PhD, master and undergraduate team, also friends, as John always jokes about me, you have an army. But I mean, although several people only, but right now I'm delivering the speech, but we have several animal study and human study still going on because of them. I really appreciate, and also I want to say thank you to my collaborators in cardiology, sleep, neurology, radiology, music, pediatrics, and pathology, music, again, and surely ability right lab. Those are two very fun pictures from my current lab. My two undergraduate students are soldering our boards under microscope because our boards are so small. We have to solder all of them under microscope, and also one benchtop study before the deploy onto human and also animals. We test on the chicken breast purchased from Whole Foods. So yeah, it's very fun pictures, and then I really want to say thank you to my powerful student team. Thank you. From now on, I will take questions. Thank you. Yes.
Maybe I'll just ask a quick question.
Yeah, please.
I was interested in the agricultural work, how a lot of that was contributing to open source projects and libraries. And I'm wondering how you see that practice moving forward in your research.
That's a really great question. I personally, as a researcher, I want to open source, as much as possible, code, and also even sometimes the hardware design. If you check the UCLA website, I'm the one actually presenter, hey, which part of our robot? Why? Because, as I come from the Chinese rural village, I got to know computers when I entered college. So it's a huge delay compared with my peers, right? So what I feel is like I try to open source so many resources so that people with source people, right? The keys, because our robots for agricultural robots is under $500. I mean, we will try our best to push it for the sensors, it's even cheaper for $50 or even $20, right? That's also another reason why to try to push, apart from commercialization, want to push the end to make it cheap as possible so that people can, we open source the code stuff, you can play with it, even if you don't have really so many resources. So based on in the future, based on the agency need, of course, some NIH programs are not, they don't allow us to expose, we don't, for sure, we want to expose the patient's data for sure. I mean, we don't have their names or the status, we just don't have the data, right? But overall, if we can open source the code, we will continue to do that. Also the hardware if possible. That's my actually goal, always.
How do they help you succeed?
Help me succeed. That's a great question. So I would say, since my research is very interdisciplinary, as my bioelectronics part, I need a close collaboration with medical people, right? So I need the convenient access to collaboration with medical people, clinicians, also music, people from different backgrounds. That's why I like the Atlas Institute, right? And then, so for robotic side, I mean, finally, if I get to the upper stage, I need the, for example, purchase robotics arms stuff, so that's why I need the with the financial support as well. And then overall, I need space for the lab, right? And then also students. That's why I feel like also I want to for the proposal writing apply on my sensor to astronaut stuff. So aerospace engineering will be really helpful. So essentially, first thing is expose me or allow me to have very seamless collaboration with the people from different backgrounds. That will be really helpful, Also, if because I heard it's really good that there are some already promotion for multi-institutional or large big grants writing. For example, I can write my parts. Doctors can write their parts, but then someone can polish our ideas and then put them together. That'll be really helpful because I heard that resources are already there, right? So yeah, I mean, that's overall my answer. Thank you.